Okay, today's lecture is on scoping rules and storage types in C and eventually C++, with thanks to my friends at WPI for this lecture deck. So we know that variables that we create in C and C++ can be automatic or static. Automatic variables are declared within some kind of a block. Could be a function block, could be an if statement block or a loop, basically anything where there's a set of curly brackets. In the case of automatic variables, storage is allocated for those variables when we enter the function or the block, and it's released when functions are returned or the block exits. And what this really means is these variables are being pushed onto the stack that we talked about, so the program stack, not a stack that you create yourself, but one that's part of the environment created when we run a program within our Windows or Mac or whatever operating system, or Linux. So they actually work very similar to the way parameters work. This is why we have to have an adequate stack allocated uh, when we compile, so that when the system loads, it will allocate a proper amount of space to the stack to handle all our parameters that are being pushed into functions when we call them, as well as our automatic variables. Okay? The only difference with this and parameters is that when parameters are created, the storage is allocated and initialized when we call the function, and then it's released after the function calls, as opposed to entering the block. So it's just slightly different time frame. It's not really being allocated at the curly bracket, like in a block, but actually at the function call. So before we get to the actual function body per se. It's a very fine point of distinction, but an important one. When we talk about scope, we're really talking about the visibility of a variable. Where can it be essentially seen, if you will? So identifiers are declared within a function or a compound statement are visible only from that point where we declare them, that right after the curly bracket, if you will, or wherever it may be, to the end of whatever that statement is, that compound statement or that function, which is the same way that Java works. So they're visible from their point of declaration to the end of the block in which they're declared. So as an example, here we have a function, fcn, which has a float and an integer declared. This, and then the curly brackets right here. You can't see it behind the green box there. And then the integer here, it's visible from this point until the end of this function body, which would be this curly bracket right down here. This double G is visible from this point until the curly bracket. And if we declared one inside this for loop, H, as indicated here, this one would only be visible from this point to the end of the body in which it's declared. So it would not be usable or visible outside this for loop. And that's important that we realize that when we declare something inside of a block like this, it's not going to be usable outside of the block, so we can't depend on it being there. For example, if it was a counter or something, we can't depend on it being there once we exit the loop. If we need it to be there, then we need to declare it at a higher point outside the loop, so it'll still be visible within the scope of where we're trying to use it. So that's an important concept here. Now, there are some variabilities in some of the different compilers and different systems. So in traditional C and Visual Studio, you have to declare all variables at the beginning of a function or compound statement. In other words, right after the curly bracket and before there's any executable code. Usually a good idea to always do it at the beginning of the block, whatever block you're declaring it in. Note this does not say they all have to be at the top of the program, for say like top of main. So we can declare it at any block, we just can't have any executable statements beforehand. And in general, I would say this is a good practice. In GCC, they're using the GCC compiler, you can actually declare variables anywhere in the function or compound statement, and of course they still follow the same scoping and visibility rules. And in C99 and C++, you have to declare loop variables in the for statement, but they're visible only, you may. So like the int I that you use for the loop, you can declare it right in the statement, right in the for statement. So you can say int I equals 0, for example, etc. And then they're visible only to the end of the loop body. So it's as if they were declared right inside the curly bracket, but you can't declare them there because you're using it in the loop statement. You can certainly declare it above, and then it would be part of the outer block. So if you need the value of your counter I or whatever to be available at the end of the function, after that, or at the end of the block, like the for loop, after that is terminated, but you need it in the rest of the code that's part of that larger block, then you'd want to declare it outside the for loop. Now, static data is different, and of course, as we're going to see here in a minute, the use of the keyword static will have different meanings depending on where we do it. Static variables can be declared within or outside of, or inside or outside of functions. In either case, the storage is allocated when the program is initialized. So when the program first loads into memory, excuse me, on whatever operating system, that storage is allocated, and it's not released until the program exits. So it has a little bit longer lifetime than just a function body or a loop body or an if test body or whatever. And static variables that are declared outside of functions may be visible to the linker, which that means they could actually be transferred between your C files. So we'll see how to do that in a minute. So the storage for these is set aside at compiler or link time, but of course the allocation won't happen until we actually run the program, because you may compile and link on one system and run somewhere else, for example. The values are retained across function calls, so that means if we declare a static variable inside of a function, the next time we come back to that function, that variable will not only still be there, but it'll still have the value that it had when we exited the function the last time. And this can be useful for some kinds of counters, like if we, for whatever reason, need to count how many times we called a function. Maybe you're counting how many times you called the add grade function for a particular student or whatever. We can retrain that value across the function calls. If we're going to have an initialization of one of these variables, it has to evaluate to a compile time constant. So it has to be something where either it's all like actual numbers that can be multiplied together, for example, or it has to be a pound define or something like that. In other words, it can't be initialized to value some other variable, especially an automatic variable that's not going to have a value until the program is actually running. So here's an example of declaring a static outside of the any function or anything. Static float f. Now int j is also essentially static, and in effect it's a global. And notice it says it's visible to the linker and all functions. So if this were in a particular .c file, j would be visible to all functions in that file, and potentially, if we declare it properly, could be visible to functions in other C files that are going to be compiled or linked with the C file in question. We put the word static in front of that global variable, float f. That's still a global variable, but it's not visible to linker. Basically what we've said is this is a private global. It's only available to the C function in which it's declared, or the C file in which it's declared. So it's visible to all functions in the current file, but you would not be able to have it be accessed by other functions in other .c files. And the key word for that external linkage is the word extern. So if we declared int j, for example, in funcs.c, and then in main.c we wanted to access that global variable, we'd have to say extern int j over there. The extern tells the compiler of that other file that int j has already been declared somewhere else. We're just sort of linking up with it, if you will. We're hooking up to it from the other file so that we can share the value and change the value for that matter. So I believe there's an example of that in here, but just in case, I want to mention that we use extern in the file that's not the one actually declaring the space for it, but the ones that want to be able to connect to it, if you will. Okay, then inside this function here, this fcn, we've got a couple of regular automatic variables declared, I and g, and then there's a static double h. So now statics declared inside of blocks we can't extern, we can't make them available to other functions in other files. But what this does is it means that next time I call fcn, whatever value h has as a result of any operations we do inside this function, that value will be retained, so we can reuse it, we can add to it, we can do whatever we want with it, but it'll be retained across the function call. Unlike I and G, which will go away. As soon as we hit this closing curly bracket, they'll go away. And if we call the function again, they'll be recreated, reinitialized, and used throughout the function until we get to the closing curly bracket again. So this is just going through what we just talked about. Here's the static storage class. Anything you declare outside the function is always going to be a static variable. Just when we put the keyword static on it, we're limiting its scope to just the current file as opposed to any files that we link with. That's what it's talking about here when it talks about the not visible to the linker part. And then we just talked about these. The ones in here are not visible to linker either, and they're only really visible inside the function, even though the value may be retained from one call to the next. You might call those local globals, if you will. In general, I would say that these kind, although you don't need them all the time, they are very useful. Again, as we've talked about before, we're going to be very careful about global variables, especially these ones that are visible to the linker, because that means other files can access them, and we have very little control, especially when we're working in a multi-person project, over what's being done with the values of that variable, when they're being changed, etc. So that can create some very interesting bugs that are very, very hard to find. So here's how we would show in another file linkage with a variable that's already been created, a static or global variable that's already been created. Here's that extern word. So in this case, extern float p, we're not going to allocate space for that when we encounter this line. This means that it's defined in another, it says program here, but it really means program file, not a separate program, not a separate main. But another file that we're going to link with when we link whatever file this is included in to make up our complete program. So no new space is going to be allocated. We're just going to get access to that space, almost like it was a pointer, if you will. Now we don't have to use any kind of pointer notation, but almost like it was functioning as a pointer. We're just connecting it. So it's already been declared. We just want to be able to use it. So a lot of things are externed so that we can use them across multiple files. In the standard I/O header files and stuff, there's a bunch of variables that are externed to point to the different standard error streams. A lot of times you see these externs included in .h files. Remember that anytime you have an extern, though, it has to actually be declared outside a function in one of the C files in order to be able to extern it in other files. So that's an important piece of notation. Okay, obviously you can't ask any questions during this video lecture, but be sure and review this and then be prepared with your questions at the next class period. Thanks.